Good afternoon, everyone. Just while people dribble in, I might just give a brief corporate blurb about Bitnami. Not many people have heard of us. We make software images. We're a smallish company. We make software, package it up so it's easy to install. In particular, we populate most of the images on the big clouds are actually produced by us. So Amazon, Azure, Google, each have a marketplace. You go, you click a button, you get a VM running WordPress or MySQL or a LAMP stack or something. Most of those images are made by us, and that's what we do. On the Kubernetes side, we're one of the big players in Helm. Most of the Helm charts come from us. If you have a cloud that you'd like to encourage people to use more of, then come talk to us. We're trying to help people with the empty cloud problem, trying to get that step from, I've provided a cloud, but no one's using it. And we try to make it easier to take that first step for users to come onto your cloud and start consuming it. Anyway, that's enough corporate talk. Right. My name's Angus Lees, or Gus, and I'm an engineer at Bitnami. And in case you're in the wrong place, this is a talk about Kubernetes on OpenStack, where I'm going to go into a lot more of the details about how the two projects interact and where. And yes, this is not a talk about OpenStack on Kubernetes. That'll be the Collar talk or the whatever other project somewhere else. People just arrive a minute later. All right. So just so that everyone's on the same level here, Kubernetes. Kubernetes is an orchestrator for containers. It runs containers. Just since this is an OpenStack crowd, to sort of explain it and how it differs from OpenStack at a very high level, Kubernetes is about applications. OpenStack is about machines. It provides a machine-level abstraction. Kubernetes, on the other hand, provides an application-level abstraction. You don't provide an operating system image. Instead, you provide the binary you want to run, or really the container, the file system you want to run. So you say to Kubernetes, here's the command I want to run. Here's the command line arguments. Here's the environment variables I want to run it in. Now you go and run it somewhere. Okay, so it's much more application level. Unlike OpenStack, you don't have the opportunity of bringing your own network address. You can't set up your own private network. In Kubernetes, Kubernetes gives your application an address to use, and that's it. Doesn't get a choice. These are some of the big differences between OpenStack. Also, because you're telling Kubernetes what it is you want to run, you can also tell it application-level concerns, like health checking. How should I know if I'm running correctly? How should I know if I've deadlocked or crashed? And so it's time to restart me. On OpenStack, the OpenStack cloud doesn't know these things because all it knows is it's running a machine. On Kubernetes, you know you're running an application. You know what port it's listening on. You know what URL you should send to that port, or what HTTP query you should send to that port to see if it's running. You know when that process exits. You know if it exits 0 or non-zero. So you can do a lot more application-level things about when should I restart. Am I healthy right now? And then Kubernetes does these things automatically. So again, when an underlying host dies in OpenStack, OpenStack will know it's dead, but typically requires a human to come in and tell it to drain traffic off there and restart, recreate those VM instances on another bit of hardware. Kubernetes, on the other hand, is much more dynamic, much more active in managing your containers. When it stops answering health checks successfully, it will kill and restart it. If a node goes away, it will reschedule those containers on other machines automatically. So it's a lot more automatic in handling machine failure. They're kind of the main high-level differences. Multi-tenancy is much less of a mature story in Kubernetes compared to OpenStack. And to be honest, the attack surface is a lot greater. In Kubernetes, you're sharing a kernel. Fundamentally, you have the same Linux kernel that is shared amongst all of the hosts, all of the containers that are running on that host. So that means they all have to be Linux. They all have to be the same kernel version because they are the same kernel. And it also means, from a security point of view, your attack surface is that whole kernel. Okay, so this is, if you're paranoid, that's a pretty big attack surface. Compared to OpenStack, where you're providing a machine abstraction. Each machine could be running a different operating system. You can have Windows, you can have different versions of Linux. And that virtual machine abstraction is actually quite small. When it comes down to the bottom, you've got disk, you've got CPU, and it's fairly restricted in what it can do. So it's much easier to strongly isolate that. And then other than that, it's got abstractions for all of the high-level things you need. There's an abstraction for load balancers, an abstraction for remote storage, for these sorts of concerns. And then the only other difference, which is interesting to this talk, is that Kubernetes is implemented mostly in Golang, whereas, of course, OpenStack is mostly in Python, which matters if you go and look at the code, obviously. So there, for the purposes of this talk, that's our main description. And of course, here's the, this is actually taken from the Wikipedia page. So this is a standard diagram of Kubernetes. You'll notice, for this talk, we want to talk about the master control node, the green one up there, has an API server. That's a lot like the Nova API server. It's basically just a web server. It takes user API requests coming in, and it talks to storage. In Kubernetes case, that's etcd. So etcd is a distributed key value database, which means it has keys look a little bit like a file system, /separated keys, and you can have a value for each of those. So it's like a big hash table or a dictionary. It is not SQL. You cannot do select every row where this condition is true. You can't do those sorts of queries against it. You can only do get this key, set this key, is this key set to this value. You can only do key level operations. It's also distributed. So etcd has a very strong high availability story. It uses Raft, which is a Paxos-style consensus algorithm. So the usual sorts of things. You need a majority of nodes to be up. So 2 out of 3 or 3 out of 5. They're your normal sizes. Nodes need to be up, and then so you can have that extra 1 or that extra 2 can be down, and everything can keep functioning and keep storing data reliably in etcd. So it's a very strong high availability story. Also on the master, you have a couple of other jobs, the controller manager and the scheduler particularly. And they are controllers that talk to the API server and that manipulate objects in etcd via the API server. And they're the ones that are trying to take actions to make the system work. So the scheduler is obviously choosing which machine a given pod should run, and the controller manager is handling lots and lots of different control loops. When you create a new deployment, it's the thing that notices and creates the replica set and then creates the actual pods to run as part of that. On the nodes themselves, you have a kubelet. That's a little bit like the Nova compute agent. Kubelet talks very closely to whatever runs your containers, which is mostly Docker daemon, but there are other alternatives out there. And so the kubelet talks very closely to Docker and tells Docker what to run and detects when it's failed and what to do again. So it's very, very tightly integrated with the Docker daemon on that host. And then you have kubeproxy, which is used to sort of do a bit of a mesh network. When a container wants to talk to a service, it instead talks to the kubeproxy, and the kubeproxy is like a load balancer running locally on that node. It knows where the endpoints of that service are. It knows which ones are healthy. It knows where to forward the request. So at a very high level, you end up with sort of like a mesh network. Each node is going directly to the healthy nodes where that service is held right now without a sort of centralized load balancer point. Pods are where the containers run. A pod is a collection of containers that are running in the same network namespace. So they each have their own file system, their own idea of slash. but when they talk to local hosts, they're all sharing the same local host. So a pod is a collection of containers which always run on the same host together and can refer to each other's services using local host ports. So it's good for, or they can, because they're running on the same host, they can also share mounted file systems. So you can have a volume that's mounted by multiple of them. So it's good for things like, I have an Apache server, and it's writing logs. Those logs are going to a shared volume. And then I have what we call a sidecar container, or have another container within that same pod, and it's running log stash or something. So it's collecting those logs and then passing off to something else. But the log stash and the Apache are both separate containers. They're separate binaries, separate, one might be a Red Hat-based container, one might be a Debian-based container, and yet they're both interacting through that shared volume that's on the host there. So that's the idea where that comes in. All right, that's enough about Kubernetes. For our purposes, here's a slightly different version of that diagram. This highlights all of the interaction points where we talk to the underlying cloud, which in this case is OpenStack. So you'll see we have the important ones are from the kubelet on the hosts and from the controller manager. They're the main ones. We have a less significant point in the API server, which also talks to the cloud. So they're making OpenStack API calls through the code we're about to talk about. Okay. Networking is an interesting part of Kubernetes, so I wanted to spend a little bit of time on this. East-west networking, or pod-to-pod networking. Every host gets allocated a subnet. Pods that are running on that host get an address allocated from that subnet. So from a networking point of view, all you need to do is make sure that subnet gets routed to that host. And the subnet for this other host gets routed to that host. The subnet for that host gets routed to that host. That's all you have to achieve. Very simple. Lots and lots of ways of doing that, which is why if you're working with Kubernetes, you'll notice there are lots of potential solutions for this. And it's common for people to get overwhelmed by choice at this point, because there are so many ways of routing packets, so many ways of orchestrating, arranging the routing of packets, that there are lots of different products out there to do this. But the fundamental job they have to do is very, very easy. If you were a large deployment, if you were hundreds of racks, 1,000 racks, you would have a system in place where you would manage the life cycle of those machines. I would strongly recommend you use static routing. It's that simple, right? If you are highly scalable, you would just allocate as part of your address allocation scheme. Machine number 4 on rack number 27 gets automatically this subnet allocated to it by maths, right? That's how simple this problem is. So I'm going to mention it several times in this talk. Don't get carried away with Kubernetes networking. It is very simple. It's also layer 3 only. So each pod gets an address. They don't get to choose their address, which means there are no overlapping addresses, unlike OpenStack. Every pod has a unique address, which means we can do network policy simply by IP tables firewalling. There's no fancy stuff we have to worry about. There's no isolated L2. There's no overlays. There's none of that sort of stuff because it's just level 3 networking. Layer 3 networking. Yeah, there is an internal DNS service. So every pod can look up a service using DNS, which makes it very simple. And that's mostly it. Yeah, the cluster IPs, which when you look up a service and it's an internal service, you get back what's known as a cluster IP. That is a sort of an anycast address, which is handled by the local kube proxy. So when you go to a cluster IP, you only ever go to the local kube proxy, and it catches all of those IPs for that node. So a particular service will have an address, and it'll be the same address for every pod that resolves it. But whenever they try to connect to it, they're just going to go to their local kube proxy. Okay? So it's sort of roughly similar to how the metadata service works in OpenStack. The metadata service, every VM appears to get the same address, but when they connect to it, some magic happens, and they each go to a unique metadata lookup. It's a little bit like that. You connect to the same address, but it gets terminated by the local kube proxy that then knows how to forward it off to where that service is right now. All right. For internet to pod, Each pod is assumed to be able to access the internet. You could obviously set it up where that's not the case, but that's sort of the assumption. That's how most Kubernetes clouds are set up. And so pods will often just assume that they can fetch something from the internet, or the Docker daemon on the host will assume that it's able to download a Docker image off Docker Hub or GCR.io or something. For ingress, there are two types of service. One is a node port service. This opens a port on every node in your cluster, and the same port. So I might have a service that I call MySQL, and I say it's type equals node port. Kubernetes will then go and allocate a port, and it's from a high range that's not going to conflict with other things. So I might end up with port 30,027. And so then I can connect to port 30,027 on any of my hosts, and the kube proxy on that host will catch that port and forward it off to where a healthy MySQL is running right now. An extension of that idea is the LoadBalancer service, and this is again where the underlying cloud comes in. The type equals LoadBalancer knows how to tell the cloud underneath how to configure a load balancer. So on OpenStack, we're configuring a Neutron load balancer as a service, load balancer. And then that load balancer will in turn use the node ports as backends, and then that will again go to the service. So I'd create a load balancer with a port open on it. It might be 3306, I get to choose this time. And then when I connect to that, it's going to forward to a node port somewhere on a machine, and that node port is then going to go to my service, which is MySQL in my example. Okay, so we'll come back to type equals load balancer later on when we talk about the actual load balancer code. Right. You all now know about Kubernetes. In this talk, I'm going to go through the actual, I'm not going to show you lines of code, but I'm almost going to do that. We're going to go through each of the points in the Kubernetes code base that know about OpenStack. Okay, so this is Kubernetes code base. This is Go code. It's part of upstream Kubernetes. And it knows how to make OpenStack API calls. And I apologize up front. This section is all the things you're not meant to do in a talk. They're fairly information-dense slides. There's not a big story. It's really just, here's what happens at this point in the code. So I apologize in advance. That's going to be fairly hard going. As a reward at the end of it, I'm going to try to wrap it together at the end and say, here's sort of an overall architecture of how, I would recommend you do a basic Kubernetes on OpenStack deployment using what we now know about how it actually works. And then right at the end, I'm just going to talk about the future directions. There's a lot of stuff in flight at the moment, so if you look at Kubernetes 1.8 versus what you see on the master branch right now, that's going to be 1.9. And if you look at some of the older versions, there's quite a bit of high rate of change here. So I'm just going to give you some idea of where we're going with those changes and what you might see in older versions compared to newer versions. Okay. So in Kubernetes, there is the idea of a cloud provider. And this is the place, the main place, where knowledge of the underlying cloud exists. It's an interface, a Golang interface, that then gets implemented by a bunch of different modules. There's an OpenStack one in that location there. And if you go and look in that directory, you'll see a bunch of others. There's one for GCE, there's one for Amazon, there's one for, I don't know, a whole, but there's 15 or so. I haven't counted, about a dozen. Including some sort of test-only ones like Vagrant and things like that. This is enabled via these two flags, and you run the kubelet and the API server and the controller manager with those flags, and that tells it to use the OpenStack plugin code, which is already part of that binary, and then there's a configuration file that can be anywhere on your disk that configures that provider. The OpenStack one has been part of Kubernetes for a very long time. This is where I get to tell a story. So I used to work for Google for a long time, And then I wanted to do something new, so I left there and joined Rackspace to work on OpenStack. And I wanted to learn about OpenStack, and so I decided I wouldn't just use one of the standard deployment tools. I tried to install it myself so that I could learn the components and how they interacted. And I looked at it and went, well, this is a Python web server, this is a database, these are just basically some processes I need to run. From my Google experience, I know how to do this. I want some sort of a cluster manager. So I looked around and I found Kubernetes, which in those days was very, very young. And I said, right, I can do this. So I tried to set up an OpenStack on Kubernetes deployment back in 2014. Suffice to say, both OpenStack and Kubernetes were not at a point where they were ready for that at that time. And because I worked for Rackspace, the machines that I had to work with were Rackspace public cloud machines. So I was trying to run OpenStack on Kubernetes, on Rackspace public cloud, on Core OS images. I think that was a combination I was running at that point. And I gave a talk about that, I think, a long time ago. But as part of that, I accidentally wrote the OpenStack Cloud Provider plugin because it didn't have any support at that point for running on OpenStack clouds. It had Amazon and Google, and that's all, and Vagrant. So I implemented the OpenStack one, and I also implemented the Flannel host gateway backend because I wanted something to do networking on top of a private network that wasn't ridiculous. And then it sort of didn't, whatever, that bit worked, but then the whole overall stack didn't work, and then I forgot about it, left it, put it aside, moved on. And then a year later, I started getting emails from people saying, oh, this code doesn't work in this situation. It's like, oh, I'm surprised it worked at all in a situation. I'd never tested it. Okay. So a year later, all of a sudden, this was a big thing. And for the last 2 years, it's been a little odd. I sit in the Summit keynotes, and pretty much every keynote for the last 2 years has been something about Kubernetes on OpenStack. So it's, I don't know, a little odd for me to sit up the back there and say, that was my code, I wrote that. Anyway. Now there's a whole team looking after it, but until the beginning of this year, it was pretty much just me. It was part of Kubernetes 0.5, so it's been there for a long time. It's been poorly documented because I'm not very good at documentation. That's why. Here's an example of what the cloud.conf looks like. It's an INI style file. Mostly what you've got to put in there is the Keystone information, which is very familiar to anyone using OpenStack. Okay, there's now some documentation at that URL. These slides are available, by the way. You can follow through from the schedule entry somewhere. All right, let's go. The first big chunk, and this is one of the big chunks of the provider code, is the instances code base. So this knows about compute, basically. It talks the Nova Compute v2 API. And if you don't have Nova, this is not going to work. It will. I should mention, most of these auto-detect. You give it the Keystone information, and then it looks at the catalog to try to see what you have available. So if you don't have Neutron available, it'll just quietly not support all of the networking options. But otherwise, it'll keep working. So if you don't have Nova available, it would be an odd OpenStack install. But if you didn't, then this would just quietly not be supported, but other portions might be. So you could use Cinder, for example, or whatever. Most of them come down to Nova. You could use the LoadBalancer without using this API. Something to be aware of is that Kubernetes has the idea of a node name, which is the host name that Kubernetes is running on. In most of the other clouds, in particular GCE, the node name is the host name and is also resolvable via DNS. One of the challenges that we've had, particularly in the early days, but even now with OpenStack, is that we can't make those assumptions. The host name is not necessarily the instance name or the instance ID. It's not necessarily unique, even. And in particular, in OpenStack, we can't look it up in DNS. There is no generic DNS way to go from instance name to address. So we assume, and this is an important assumption to be aware of, we require that the node name is the same as the OpenStack instance name, which means all of your OpenStack instance names, if you're using this provider plugin, need to be unique. Okay? And it is not the same as the host name, and it is not the same as the OpenStack instance ID. If you look at the code, there's the idea of a provider ID, which is the OpenStack instance ID, and that gets reported on the status. So if you look at the node status, somewhere in there will be the provider ID, so you can find out what the instance ID is. But we can't rely on that in the code. The provider ID we find out from running on the kubelet itself. We do a metadata service lookup or config drive. So that's one of the bits of code that is called from the kubelet directly. So an important part of this is the node address resolution. So just to give you an idea of what this code looks like, Kubernetes says, here's the node name, what's the address? And so in our code, we have to get the node name, assume it's the same as the instance name. We do a Nova lookup for that instance name to get back all of the servers that have this name. If we get back anything other than one result, then we throw an error. If we get back one result, we say, aha, this is the instance we're talking about. So now we look through the addresses on there, and we try to sort the addresses in terms of internal and external. So it's a bit of a guess based on whether it's got the floating IPs type, or particularly for Rackspace case, if the network name happens to be public, which is how Rackspace did their public cloud networking. But if you're running a network, if you're running a cloud and you call your network name public and it's not public, you deserve everything you get. The access addresses are always considered external, and so then anything else is considered internal. So we build a list of the addresses that we found, we sort them by internal and external, and in this case we bring back the first an arbitrary choice of internal address. So that's how we do the name to address lookup. If there's no internal addresses, we pick an external address. This includes IPv6 addresses on OpenStack. Kubernetes is not particularly IPv6 ready. It's sort of half there, which is to say it doesn't work. Bits of it will work, bits of it don't work. We were one of the first people to introduce IPv6 addresses into the Kubernetes code base. So one of the things we had to do early on was go through all the places that built URLs and say, you can't just go address : port. You've got to properly quote the address with square brackets because it might be IPv6. So we had to change all that code to use proper URL construction functions rather than just naive string concatenation. So even now, I would recommend not putting IPv6 internal addresses on the network that is just there for provider nodes, unless you want to help work on IPv6 support in Kubernetes. And then one other thing that happens is the flavor. We get the instance flavor, and that ends up on a label on the node. That's not very interesting, but that's another thing that happens in this bit of code. All right. That was the hard one. Zones is a much easier one. Zones just looks up the availability zone and the region, if you've configured a region, and they turn up as those labels in Kubernetes. And then when you're working in Kubernetes, you can say, I'd like to only schedule this pod on nodes that have this label. So you can say, only schedule this pod in this availability zone. You can also do anti-affinity sort of rules where I'd like these 3 replicas of this pod to be spread across availability zones. So this is where these labels come in. And then very recently, there's a new bit of code there to do that for remote nodes. The original code does that, again, by looking up the metadata service on the local kubelet. Load balancer. This is the other big chunk of code. This requires Nova and Neutron. It supports LBAS version 1 and version 2 until last week, 2 weeks ago, when the version 1 code was removed. But up until now, it supported version 1 and version 2. What this does is so in Kubernetes, you have a service object, and if you say type equals load balancer, it configures the underlying load balancer. For OpenStack, this is a lot of steps. So we create the load balancer, we do security groups, both on the load balancer itself and on the nodes. So there's load balancer to node security group, and there's a public to load balancer security group. We support the client IP service affinity feature, but not other variations. We set up the member pool. We put all the backends into there. Remember the discussion about node ports? This is where the node ports come in. We create a monitor for each of those, so the load balancer will do health checking of those nodes. And in most cases, you want your load balancer to be publicly available, so we also allocate a floating IP and more security groups. Yeah, so there's a lot of steps in here. There's a lot of code. Any one of these steps might fail. So all of this code has to be ready to deal with the half-configured case. If this code fails 7 steps in and then gets called again to retry, the first 6 steps will already have succeeded. And so each of those has to say, is there already a load balancer called this? Oh, yes, there is. Right, I won't create a new one. Is there already a member pool called this? Oh, yes, there is. Right. Does it have the right members? Oh, wait, yes, some of them are right, some of them are wrong. We'll have to fix that up. So all of this code is quite complex and has to do a kind of a sync with what happens to exist right now on the cloud. So it's quite a bit of code. This one I really like, but no one knows about. Routes. There is a feature in Kubernetes called KubeNet networking. This implements pod-to-pod networking within Kubernetes itself. So it does address allocation within Kubernetes. The subnet allocated for each host is just made up by Kubernetes within a larger subnet. And then it uses KubeNet to set up the routing between hosts. So if you enable this feature, you just tell it which neutron router you have on your worker nodes. Sorry, your worker nodes are all in a neutron private subnet, private network. You tell it what the router is for that subnet. And then it will use the extra route extension to just configure routes in the routing table. So it'll say, hey, the pod subnet, this pod subnet has to be routed via that host. This pod subnet has to be routed via that host. And so it sets up all these routes, and you basically get working Kubernetes networking with 0 overhead. It's just packet being routed directly. There's no encapsulation. And if you're using something like Neutron DVR or some other distributed neutron routing solution, then the packets are being sent very efficiently all to the right hosts with 0 configuration overhead from your point of view. Note, however, KubeNet is deprecated. The new feature is CNI, networking plugins, so this feature will probably be obsoleted before anyone even knows about it, which makes me sad, but anyway, it's there. All right, now we have 2 bits of code that are not part of the provider plugin. They use the provider to get Keystone sort of credentials, but the code lives elsewhere inside the Kubernetes code base. The first one, which is much larger, is the Cinder volume plugin. So when you mount a persistent volume, you can mount it from just about anything that you can run a mount command for. If you're running on top of OpenStack, you have an extra step. You have to attach the volume to the VM, and then you can mount the device. So this is the code that knows how to do that. When you say you're doing Cinder, you give it the volume ID, and this code goes, aha, I know what to do, talks to Cinder API, connects it, attaches it to the VM, then finds the right host address, host device that magically appears. And that's actually a lot harder than it sounds. You have to guess, basically, which is a little disappointing, but that's what you have to do. So we have some code there for particular ones that knows what dev by ID file name to look for. And then it mounts it, makes it available. It actually does a double mount. It mounts the device into a central location and then bind mounts from that location into each pod. And this allows it to do some of them bind mounted, can read only, whereas some can be read write, because you can do that through the bind mount. There's also support there for dynamic provisioning, it's called, which will create new volumes on the fly. So when you say, if you've configured the provisioner, it'll say, I want a volume of 10 gigs, and then this will actually tell Cinder to create a whole new volume of 10 gig size, and then make that available on the fly. And then, by default, delete it again when you're finished, although you can say you don't want to delete it. This code lives somewhere else in the code base. I put pointers to the code base in here because if you're going to be using this stuff for real, you should probably at least look at the code. It's not that hard to read. Go code, even if you don't understand Go, as long as you know what an if-else branch looks like, you'll see what that looks like in Go. It's pretty easy to read. It's about as easy to read as Python. So you can go in there and just read through, and you'll be able to see, oh, I see, in this particular case, it's looking for this particular annotation, or this particular string, or this particular combination of options. Now I understand why my configuration isn't working, or now I understand why it's giving me that error message. Okay? It's worthwhile just knowing where to look. Kubernetes codebase is huge, but if you know where to look, it's pretty self-contained. It's actually not too bad. And finally, the last thing here is the Keystone password auth plugin. This is mostly a terrible idea. I've really only got this in here for completion. What this will do is it sets up a username and password authenticator, which authenticates against the cloud.conf configured Keystone. So if the username and password verifies, if Keystone's able to authenticate that, then it says, yes, Kubernetes, go ahead and use that user. That's a valid password. Anyone who's from the Keystone community here, I apologize. This is not the way Keystone is meant to be used. If you use it this way, what you're doing is sharing your password with all of that Kubernetes code, whereas what you're meant to do with Keystone is talk to Keystone separately, using username and password, perhaps not using a password, perhaps using two-factor auth or Kerberos tokens or all those millions of features and different options that Keystone supports. And then you're meant to get back a token, and then you pass that token onto Kubernetes in this case, and then Kubernetes can verify that that token is valid. That's the way you're meant to use Keystone. That is not what this code does. So, now, every now and then someone comes along and proposes some new feature here, and we say, no, this isn't the way Keystone is meant to be used. Do it this way. And they say, OK, and they go away and they come back with the token version. And then we say, no, just use the webhook support. So there's been about 3 actually pretty complicated patches that have gone through that path now and then just withered and died. So if you want to do this properly, the way to do it, use the existing bearer token support. There's support just for arbitrary bearer tokens in both the kubectl command line and Kubernetes server side. And then you do a webhook authenticator authorizer, which will get called every time a new request comes in, and it'll say, hey, is this bearer token valid? And then you add a little bit of code that answers that webhook request, goes off to Keystone, verifies it, comes back with yes, or whatever other policy you want to put in place. Okay, that's the way you should do this. But anyway, that code's there if you want it. The other thing, people come along with this request often, and they say, we want better Keystone integration into Kubernetes. And it takes a little while to kind of tease out what they actually want when they say that. Some people are of the mistaken opinion that this will give them multi-tenancy. This does not give you multi-tenancy. Okay? All the code we've talked about on previous slides, when it talks to OpenStack, it talks as the user that is configured in cloud.conf. Okay? So if you create a load balancer, you're creating it as that user. You are not creating it as the user who sent the request to Kubernetes. Okay? So all the resources that are created and managed by Kubernetes are all owned by the same user, the same OpenStack user. So you don't magically get some sort of idea of multi-tenancy and of honoring the identity down the stack. You don't get that by using any of these features, I'm afraid. It'd be nice if you did, but you don't. Okay, so that was the hard slog part. Now, just quickly, I'm going to go through the end bit here. There's not a whole lot left. The first thing here, how not to set up your own Kubernetes. The easy thing to do is to use something like Magnum. Single click, you get a Kubernetes cluster running. Okay, it's just like GKE on Google. Magnum works really nicely if it's available on your cloud. There's a bunch of other tools. I didn't even try to list them. Kubernetes has never really had a standard tool deliberately. There's never been a standard installer. So there's been lots of different installers that are optimized for different situations. you'll find, yeah, Chef, Puppet, Ansible, whatever other favorite orchestration tool will have some configuration already out there that you can use. Cube Spray was one that was mentioned earlier today. That's a good choice. That's an Ansible set of Ansible scripts. Just a word of warning I'll put on here, OpenStack Heat. In the Kubernetes code base, there's a thing called kubeup, which is a shell script which goes off to a whole bunch of salt configurations for different clouds. In there, you'll find something called OpenStack Heat, which is a bunch of Heat templates for installing Kubernetes on OpenStack. Don't use it. It's basically, it worked when it was first proposed and merged, but it's been effectively never maintained ever since. So it's not what you want to build your production install around. So here's what a deployment looks like. Kubernetes, as we've said, doesn't have a strong multi-tenant story. So I would recommend doing what GKE does and have one Kubernetes cluster per hostile tenant, right? So if you're a private cloud case and you want separation just for administrative reasons, but you're not really concerned about actually trying to exploit each other, then by all means, one cluster, give everyone a different namespace, everything will be happy. But if you're a service provider and you're trying to do, legitimately hostile users on the same cloud, you're very, very brave if you try to run them all in the same Kubernetes cluster right now and perhaps ever. I would recommend doing a dedicated cluster per hostile tenant. You want to have 3 controller VMs. You need at least 3 because of the etcd quorum requirement. Okay, you need to have a majority. You need to be able to survive a node failure and still be able to form a majority. So you need 3 or 5 if you're being really paranoid, but 3's quite normal. Or 1 if you're doing a toy setup. If you're just doing a demo, you don't care about availability. Then you need a bunch of VMs for your worker nodes. You want to put them all in the one Neutron private network, and then use that private network as your isolation, right? Don't mix that with other things. Keep it reasonably isolated just for this purpose. And then whether you want to spread those across 2 or 3 availability zones depends on your workload. If you just want to be able to survive a single zone failing, then you only need 2. But if you want to give your users the ability to run something like etcd, where they in turn need a quorum requirement, then you'll have to give them 3 zones. And then in general, once you're past that minimum requirement, generally you want fewer, larger virtual machines, because they'll be able to use the memory and things more efficiently. They'll be able to pack more containers onto one node, and you'll waste less RAM. If you have lots of machines with a small amount of RAM, you're wasting all those rounding errors. And so the sum of the amount of RAM that you can't use is going to be much more in total than if you had fewer, larger VMs. And then you want a LBAS load balancer pointing to the API server. This is kind of used to bootstrap the whole system. All the kubelets need to know, how do I talk to the API server? So they all have the address of the API server on the command line, effectively. So they need to have a known point where those kubelets can connect so that they can talk to the API server, so that they can then discover everything else. So the easy way to do that, if you're on OpenStack, is just configure an LBAS load balancer manually for that purpose. And then if you want to provide other services on top, you'll need those other things we talked about earlier. LBAS and Cinder and floating IP networks. Again, a little bit here about networking options. This is a common question that I get, so I've put a slide in here about this. There's lots of choice available, and people get overwhelmed by the choices for Kubernetes networking. So in particular, if you're on a dedicated Neutron private network, you've already got security, you've already handled how do I get my packet from A to B, it's already handled for you by the Neutron network. You don't need another overlay on top of your overlay. Okay? So avoid things like flannel and weave. These are normally the default options on deployment tools because they are the most general purpose tools. They will work in just about every situation because they have because they are an overlay network. Okay? But we're not a general purpose situation. We are Neutron private network, and that's all we care about. Okay? So don't use those tools. Instead, you should use KubeNet, except it's deprecated, so sad. Or Flannel Host Gateway, which again I wrote specially for this use case. It assumes all your nodes are on the same L2 network. It's good for the private home network case or the smallish private cloud case. And it's also good for the OpenStack Neutron case, and it just does direct routes. Does that same thing that Kubernetes does, but does it via Flannel. So it uses Flannel is able to use the same etcd as Kubernetes, so it's a very easy install. And then the host gateway backend will just set up routes. It'll again say that subnet goes over there via a direct route to that host, and that subnet goes over there via a direct route to that host. And if you look at your host routing table, you'll have a route for every single node on your network. So it's direct host-to-host routing. Very simple, works very well, zero overhead. It'll scale to, I don't know, 1,000 hosts or something by the time it starts to slow down. It'll scale as big as the Linux routing table will scale. Another interesting option is Calico. A lot of big networks use this, and I sort of understand and sort of don't understand why. If you're a really big network, as I said, just do static routing, in which case you're probably on bare metal and you're probably not interested in this particular conversation anyway. But Calico is an interesting option. It uses BGP to effectively do host routes in the same way, but it uses BGP to signal those routes. And it supports a few other options like network policy firewalling and things, which people like at the enterprise end of things. Again, remember, Kubernetes networking is all layer 3. So it's very simple. If someone comes along and starts talking about isolation and layer 2 and overlays, you just say thanks but no thanks and you walk away. Okay? Lots of people are trying to sell things in this space. Simple, simple, simple. All right. So I'm over time, aren't I? Or whatever. There's a more lengthy cloud.conf. In particular, I've turned on a bunch of the load balancer options, which are off by default. We should probably fix that and just turn them on by default. That's what it looks like. There's some pretty good documentation for this now. Oh, the last one. If you're deploying right now, if I was giving this talk in a year, I wouldn't bother including that last line. But since I'm giving the talk right now, you need to know about that last line, which fixes the block storage version detection. We only support version 1 and version 2. We don't support version 3 yet. But the way version 3 appears in the catalog is a bit different, and it confuses the auto detection code. So you just need to bypass it to say, hey, don't do auto detection, just use Cinder version 2. It's been fixed. It just depends on what version of Kubernetes you're using right now. If you want to enable the Cinder Auto Provisioner, that's what it looks like. That's the Kubernetes API object. So you do kubectl create -f, that thing. The key line is provisioner, that string. And if you want to make it the default persistent volume class, you add the annotation above that. And there's a few parameters supported. They're not many. You can tell it what availability zone, and you can tell it what Cinder type you want. And here we're pretty much done. So the things that are happening right now, we're trying to make fewer options and be more automatic about things, which is great. I am thoroughly in favor of all of this. And Feng Yunpan's doing a lot of this work, and yay. We're moving more cloud.conf options to per object annotations. In the past, everything was in cloud.conf, and you weren't able to change that per object. Some things like load balancer options, you really want to change per service. So some of those have been moved across, and more of them are being moved across into annotations. And the really big changes underway at the moment is moving all of this code out of Kubernetes. There's too many cloud providers now, and there's more coming along all the time. So they said, wait, we're going to move all this out into external repositories and have a common core that can talk to any of you. So this is called the external cloud provider. It's a big project. It's a big refactor of code. DIMS has been doing a lot of this work from the OpenStack side. It's not ready yet, and it's a big project. It's made some good progress. They haven't dealt with the in-kubelet case, and I'm not even sure they have a good answer for that right now. That's one of the more complicated bits. And this is the last little bit down the bottom there. If you have any questions about this, if you want to talk to any of us, if you want to help out, if you want to contribute code, in particular right now, we'd really like some help with automated testing and that sorts of work. And of course, documentation, because I'm crap at that, so it's not people. And this is where you can talk to us. In particular, the Slack channel, that's the main communication channel, really, for this small group of people who's working on this now. Thank you. My name's Gus. I'm around for the 3 days. I imagine there's lots of questions about this sort of stuff. I'm very happy to talk to them about them. Just come and find me. I'll be wearing the nice subdued shirts.